Up until fairly recently, Poundland's main automatic nightlight was based on a tungsten lamp. You can see it just tucked down the end in here. It takes a E14, that's the base, 40mm diameter, 7-watt lamp maximum. And it's worth noting that it never runs it at full power. Because of the way the circuitry works in these, it's usually based on this very simple thyristor circuit. And it shimmers visibly. I don't know if actually, you know what, maybe I'll be able to show you this. It's got its pin sticking out the back, so maybe we can plug it in here and cover. Yep, see how it's flickering on the camera? That's because the lamp is being turned on and off effectively. It's only lit for half the cycle. The replacement, which happened recently, is based on an existing style of LED lamp, which I think is going to be a resistive dropper inside. That, I don't know if there's any smoothing. Let's find out if there's any smoothing or if this one's just as flickery, if I can actually make it light. It's very sensitive. Well, there it goes. It's going to show a bit of flicker because there probably isn't any smoothing, but it will spend most of its time lit because of the type of circuitry. Let's open them up. So there's the old tungsten one. Let's dump this out of the way. And a pair of scissors into this other packaging for the super spivvy new LED one. Now, I have done some tests in these and it shows something quite surprising. This one draws about 3.7 watts and it draws 20 milliamps of current with a power factor of about 0.7 when it's lit, because the use of current is skewing the result because it's only illuminating in half the sine wave. This one, on the other hand, draws about a quarter of that. It only draws 0.9 watts, 4 milliamps, and it has a slightly better power factor, 0.8. But the really interesting thing is that because of the way they work, this one only turns on the lamp when it gets dark. This one actually shunts out the LEDs when it's light. So this one, although it draws only about a quarter of the power, it draws it all the time when it's lit and when it's not lit. So when you put it side by side, although this one's drawing 4 times as much current, if it's only lit for about 8 hours a night, then this one actually draws exactly the same amount of power overall as this one. But theoretically, I was going to say, theoretically the LED should last longer, but you just never really know. What sort of screws has this got? Weird screws. It's got triangular screws down here. What's this one got? This one's also got triangular screws. Right. I'm going to have to see if I can find a screwdriver that's going to fit that. I'm not sure if this is going to do it. This does have a triangular. That's not triangular. This is. And I've also got this of the pure triangular, but I think it's tri-wing. Let's give it a go with the tri-wing and see what happens. It's just spinning. This is where I chew up the screwdriver because I don't necessarily have the right type, and it's one of these anti-tamperish type ones. It's coming out. I shall use brute force to drive the screwdriver tip in to get that started. This one's also notable for having a fuse. That's not really surprising. These small lamps do have a tendency to go with a bit of a pop because there's such a small compact space inside. I think that's just an ordinary screw there. Normally if you're changing the lamp, you just undo this screw, tilt the lid down. Is that how it comes out? Let's try this. Let's pretend we're trying to change the lamp. So here's the lamp. I have to say, it's quite a good source for one of these lamps. They're quite unusual. 240 volt, 7 watt. But the main thing about these is because they're not really being run that hard, it's going to last a decent length of time. But when you have such low power lamps on a 240 volt supply, the filaments tend to be very, very weak. They tend to be very easily broken. Let's see if we can get this further apart then. I think I see some clips. My stomach is bubbling away here. I hope it's not audible. That's because I've just made a video in which I ate a selection of hot dogs. That's not some smutty sort of Pornhub type thing like that. It is actual hot dogs that I cooked in the electric hot dog blaster, the one that electrocutes the hot dogs. This is, oh, there's a sticky label on the bottom. That's part of what holds it together. here is the circuitry. Ooh, there's a little capacitor down there. That's interesting. So the arrangement in here is that one of the contacts comes straight up to the top here, and the other contact goes via the fuse onto this. So this is effectively just in series with the lamp. That's interesting. It looks a very, very simple bit of circuitry. Rightio, let's take a look at this one. And I shall reverse engineer these, obviously. I wouldn't leave you on tender hooks as to what's inside. Now is this one a crosshead at the top again? Because I don't know if there's any real reason for it to be crosshead. Or is it a tri-wing? I'll just force this in and spin it and see if I can get it off. I think it is just spinning. There we go. They don't really want you going into this one because this circuit board will effectively be live in normal use. Intensity-wise, they're actually fairly similar. The LED one is, rather predictably, a much whiter light because it's fitted with cold white LEDs. And it's a resistive dropper. It's got a fuse. That's nice. It has what you'd expect. It's got these two surface mount resistors that are being used to limit the current. It's got the 3 LEDs in series. It's got a bridge rectifier to rectify that limited current. And then it's got a little transistor down here with a resistor which will bias it on, depending on the type of transistor. And then when the light shines on this, when it's a high enough light level, it will effectively turn that, it biases it off, and this, when it's a high enough light level, it turns that transistor on, and that effectively shunts just these 3 LEDs. It's not efficient. Most of the power is being dissipated in these resistors. That would be quite interesting to look at with a thermal imaging camera. I wonder what temperature they'll get up to. They are 30k each, 30,000 ohms each, so a total of 60,000 ohms, since they're almost certainly in, yes, well, there's one in each of the AC input leads of that. Right, tell you what. I'm just going to, I'm going to plug this in. I'm going to reverse engineer everything. So I'm going to plug this in and take a little temperature reading off it once it's had a chance to warm up. And I'm going to reverse engineer this and see if I can identify the components, because it'll be a fairly specialist thyristor in this. So I'll be back in a moment. The circuit boards have been reverse engineered. No great surprises. Let's start with the traditional one that lights the tungsten lamp. The supply comes in from the live, goes through this fuse holder, and then goes through this diode here. It's a 1N4007. That's a 1000 volt rated diode. It's just a really common type of diode. And that would then normally be blocked by this thyristor if it wasn't turned on. The thyristor is a super sensitive gate one, TP4M. Its gate is rated in the region of about 100 microamps or so. The 4 indicates around about 400 volt rating, which is pretty common for these sort of things, certainly in the UK main supply. This 2 megohm resistor seems a high value, but it's able to pass enough current to turn that thyristor on. And that is normally shunted down to the cathode of the thyristor. Let's draw these an anode. Let's draw it as K for cathode and gate for the gate. And the gate is normally pulled in normal daylight. Light shines onto this LDR, which interestingly, first time I've seen this, it's got a little capacitor across it. And that pulls the gate down to the cathode of the thyristor, turning it off. But when it's dark and this goes high resistance, then the 2 megohm resistor here can trickle enough current into the gate to turn that thyristor on. And when it does, because of the nature of thyristors, when they turn on, they switch on solidly. They turn on until the next zero crossing point of the main cycle. So it triggers, it turns on, and it latches, even though effectively at that point this lamp, which was passing some current through to actually allow that circuitry to operate, effectively comes into circuit. And that means the lamp will only light for half of this sine wave, which gives it that slight shimmer, and also means it gives a very, very long lamp life. That shimmer is largely reduced by the thermal inertia of the filaments, but you still see a very slight shimmer off them, particularly just as it's coming on, because initially it won't turn on over the full sine wave. It will just be clipping at the very peak just when that can pass enough current to turn the thyristor on. The other circuit, this one, is again very simple. Live comes in, goes through a 1 amp fuse. The 1 amp fuse is just there as an anti-apocalypse measure. It's worth mentioning though that the live and neutral both pass by this screw here. It's actually riding over one of the tracks and within about 1 millimetre of the other track. Very close. I suppose it's really that fuse is there in case liquid gets in or something and something starts burning up and it will hopefully break the circuit. It then goes through the two 30k resistors. It's purely a resistive dropper, and they get quite hot, as I shall show you shortly. Well, I could show you right now. They go up to about 98.9 degrees Celsius here. Ambient temperature in here is, not sure that is at the moment. Ambient temperature is about 12 degrees Celsius. So I would say then about 86 above ambient, so they get quite hot, but they are resistors. They're designed to run hot. Once again, I'll thank Christoph for the generous gift of the thermal imaging lenses that let me get nice close images into the circuit boards to the point you can actually see the components. It makes a huge difference with the FLIR. So those resistors get hot. It then goes through the little bridge rectifier. That's this little bridge rectifier here. Gets converted to DC. And then these three LEDs are just wired straight across that bridge rectifier. So what actually happens to turn them off is they have a tiny little transistor down here with a resistor next to it and an LDR. And that's these. Slight screw up. I thought it was going to be a PNP transistor, as many of them often are, but it doesn't really matter. If it was a PNP transistor, the LDR and the other resistor would just have their positions swapped. But in this case, it's an NPN transistor. Can't read the number on it. But it will just be a generic little thing. It's only ever going to see about 9 volts across the LEDs, and then when it turns on, it's going to clamp that to below 9 volts. So that is, during daylight, that transistor is actually turned on by the current flowing through this LDR, and that makes it shunt the LEDs out. It won't shunt them completely. It won't shunt to like 0 volts. That voltage needs to remain high enough to actually keep the gate voltage high enough to actually turn this transistor on. So it'll be somewhere in the region of 1 or 2 volts, I guess. Now I kind of want to know what voltage that goes to. Hold on. Let's plug it in and measure it. That's the best way to find out, he said, precariously jamming live things into sockets. Oh, this is already on 20 volts. Let's measure. Let's not short excessive things. Actually, I can measure what it is directly across the output of the bridge rectifier here. So the voltage, when that transistor's turned on, is pretty much, hold on, get it in, it's just above 0.6 volts. It's 0.76 here, just because all it has to be is just above the base voltage required to turn that transistor on, which is typically about 0.6 volts. Let's unplug that before I do something terrible. Noting that I could have done something terrible by slipping up and grabbing hold of it, but that wouldn't have actually had adverse effects. So normally that transistor turns on, it shunts the LEDs out, but that means that during the daylight, these two resistors are dissipating that power, which is the thing I was mentioning about how it's not that efficient. But the reason they do it is it's just the simplest possible circuitry. I've only ever come across one LED nightlight that tries to actually break the power to the LEDs. And ironically, the circuitry was so stupidly complex to actually do that. It had to derive a separate power supply for that section of circuitry and pretty much drew the same current as the LEDs. So this is just the absolute easiest. It's not a new circuit. They used to use the same thing. They used to actually have an LDR and resistor arrangement bridge to shunt neon lamps as well. Some of the earliest neon night lights that would go out during the day. It was a gimmick to make it look as though it was saving power. In this case, it's helpful because it saves the life of the LEDs, although having said that, it's only 4 milliamps going through the circuit. Think of it's two 30k resistors, that's 60k. The RMS voltage here is about 240 volts. 240 volts divided by 60,000 ohms equals 0.004 amps, which is 4 milliamps, which is what we measured earlier on. Well, which I measured earlier on. The resistor down here, the 68k, when it's dark and you want this light on, this gradually pulls the base to the sort of off state. It pulls it negative. And at the point this goes below about 0.6 volts, that transistor will turn off and the LEDs will start to light. It's just a balance between these. By changing the value of this resistor, you could change how sensitive it was when it came on or when it went off. And that just leaves one thing that I'm kind of intrigued now. The LEDs, I wonder if I've got any that would actually fit in that. Do I have any LEDs that I could put in there? If I do, what colour should I put in? Right, give me a moment. I'm just going to have a wee hunt about and see what I can find. Let's do a Louis Rossmann. I've smothered everything in flux here, as is traditional. So let's use the heat gun. I don't normally do this. It's kind of rare to use the heat gun for removing surface mount components. I normally just splat them and take them off. Okay, that's a good start. Let's put the heat gun out of the way. Now, LEDs. What can I use? I've got some really enormous ones, but I think the ones I'm going to end up using will be... I've got warm white ones. I've got the 1206 size. Do I have the... I should have some others in different sizes. I should actually have looked them out before starting this. That would have been a good idea. Right, one moment please. Okay, it's definitely gone Louis Rossmann now because solder paste and everything. Wow. First major surface mountable. It's not really a first major surface mounted thing. First time I've used the solder paste that I'm expecting everything to just slide in. That's assuming I have just applied solder paste to it and not heatsink compound. Hold on, I'm just going to check. It's an alloy lead and tin. It is solder paste. Let's get the heat gun in and see if these flow into place like all those other videos show happening. You can see the solder paste. I'm wondering if it's just blowing the LED out of the way. That's just brilliant. Why does that not happen in everybody else's videos? No, it's blowing it away again. That's shit. Right. This isn't looking very sophisticated. It's not gone Louis Rossmann after all. It's gone shitty big clad surface mount soldering. Right, tell you what, I'm going to just heat that up and jam it on. Okay, that looks relatively... It doesn't. Let's just pin this one down while I solder it. Alright, now the solder's flowed, it's better. Yeah, that's better. They're kind of sliding into place now. I'll give them a wee reflow to actually see if I can make them slide into place properly. No. Oh. Okay, that'll do. Now that everything's thoroughly chromated, I can put that back in and see if any of those LEDs survived that ordeal. Let's let that cool down a bit. Find the screw. There's the screw. Plug it in. Let's zoom back out here. Yeah, that was a disaster. Maybe I should have tried that beforehand. Done a wee rehearsal, but having said that, it's real life. Maybe I'll even have put the LEDs in the right way around. Okay. Right. That's a bit messy, isn't it? I'm beginning to wish I'd just soldered them with ordinary solder now. But not to worry. Let's plug this in and turn out the light and see if the blue LEDs light up. Yes, they did light up. Let's take the exposure off so you can see that. Oh, it's perhaps not that bright. So which is the correct cover for this? This is the correct cover, so that's what it looked like with the cover on. Yeah, that looks alright. That's quite nice. That gives that nice sort of moonlight light effect. Right, one moment please. Okay, one last hack before I put this back together. If you want it to be lit all the time, all you have to do is either cut off the LDR, or in this case I'm just going to desolder one lead temporarily, just to prove the point. And when you do that, it means that the unit will just light all the time because it thinks it's continually dark now that that LDR has been disconnected. And you'll see the LEDs have lit and they're glowing away there. So I'm going to put it back together and that should be it. All back together again. So that is the evolution of the Poundland nightlight. It's gone from that old-fashioned tungsten style that lasted so long. Worth noting, the contacts just basically sit into the housing here, so that as the lamp goes in, it rubs against the side contact and then makes contact with the bottom one here, that it just touches against it. Very simple construction. But the LED one, I'm surprised it took them so long. I wonder why they, stuck with the tungsten so long before moving towards LED. But now they have. Maybe they were just waiting for the price of this one to come down to the point they could sell it at their pound or £1.20 as it is in deals in Isle of Man. So there we go. A little bit of surface mount as well, and a nice change of light. I quite like the blue because it gives the classic Hollywood blue light effect, the sort of moonlight effect. So that just leaves one thing to say. Gute Nacht, mein Kinder.